SwayamPrabha. Digital India. Educated India.
Good morning all of you. Yesterday we were looking at one of the fundamental solutions to natural convective boundary layer flow past a vertical flat plate, and this was initially attempted by Polhausen again, and the theory behind this similarity solution is a continuation of the Blasius solution. So, we assume that the similarity variable is of the same function as in the Blasius solution. Only difference here will be that the dependence of boundary layer thickness, instead of being on Reynolds number, we suitably modify it to be a function of Grashof number. Okay. Accordingly, Polhausen chose the similarity variable something like this, and then we proceed in the same lines as we derived the Blasius equations, starting from the stream function definition and then substituting this to find the u velocity, v velocity, and also the gradients of all the velocity components. And then finally, when we substitute into the momentum equation, we end up with the following similarity equation. Okay. Similarly, if you do the a similar transformation from the energy equation, you get the following similarity equation for the temperature theta. Okay. So, here we have defined theta to be the non-dimensional temperature based on T minus T infinity by T wall minus T infinity. Okay. So, these are some of the fundamental components to deriving a similarity equation, and they are pretty much common. So, if you do this a couple of times, you will become familiar for the third time. The only catch is how do we find the right similarity variable to transform this solution. So, that is the most important point, and once you find it, either by trial and error or by intelligent guess. Okay. So, you will be able to most likely convert the PDE into a similarity ordinary differential equation. So, now you should understand that these two equations are coupled in the sense that you have this term theta which is sitting in the momentum equation, and therefore, unlike the external forced convection case, you cannot solve this separated. So, you have to do this simultaneously when you use the shooting method, and we will see that in a short time. But before that, I asked you to check whether you get these similarity equations. I hope some of you could try it. So, are you able to get the same equations? Anybody who tried so far? No? Anyway. So, I think I request you to please check, because these are all very critical part of the similarity equations. Okay, do not because substitution, if you do it a couple of times, you will understand how the derivatives are computed and things like that. So, now let us write down the boundary conditions. See, unless we write the boundary conditions, we cannot complete the we cannot say for sure that this is a similarity equation. Okay. So, the boundary conditions also should be independent of x and y. So, there are cases in mixed convection where you can get a similarity equation, but the boundary conditions does not show a self similar set of boundary conditions. So, in that case what happens is you cannot solve those equations anyway, even though they are converted. Okay. So, we have to first also ensure that your boundary conditions satisfy the requirement for similar equation. So, what are the boundary conditions here? So, if you take the case of the vertical plate, pretty much similar conditions as in the case of external forced convection. At we have the coordinate here x and y. So, therefore, to solve this we need to therefore define 3 conditions for f and 2 conditions for theta, right. So, and therefore, at when we say do this transformation from psi which is a function of x y to eta. So, we apply also the transformation for the similarity variable eta. So, therefore, at y equal to 0, since we have the no slip boundary condition. Okay. So, we can also say that at using our similarity variable eta equal to 0, right, y equal to 0, eta equal to 0, what will be the condition for df by d eta? 0. So, we have based on the fact that u equal to 0, we can say df by d eta equal to 0, and what about, can we say something else from the v velocity when v equal to 0? So, df by d eta at eta equal to 0, v equal to 0. So, therefore, f equal to 0. Okay. So, we need one more condition. Where can we apply? At eta going to, so y going to infinity. Okay. What will be the condition? Let us look at the condition with respect to y going to infinity. What do you think will be the condition? U equal to 0. Okay. So, can we also say du by dy equal to 0? So, if you draw the velocity profile here, the pure natural convection case, the gravity acting downward. Okay. So, this is 0 outside and also at the plate. So, we can say both u equal to 0 and also the derivative of this equal to 0. So, therefore, if you put the condition u equal to 0, what happens? df by d eta equal to 0 again. And if you put the condition du by dy equal to 0, d square f by d eta square equal to 0. Okay. So, now we should also remember that the condition at x equal to 0 is also part of eta going to infinity, correct. So, therefore, at x going to 0, eta going to infinity, what is the condition? U should be equal to 0. Okay. So, the x going to 0 condition is satisfied by this condition as well, right. So, these are the conditions now. Similarly, let us write it down for the thermal boundary layer. So, at for the energy equation, at y equal to 0, what is the temperature? This is the wall temperature which is constant, and therefore, correspondingly at theta equal to 0, theta will be 1, and at y going to infinity, okay, corresponding to eta going to infinity, theta will be going to 0. So, this is pretty much the same as the original Paulowson's boundary conditions, only that the case of momentum you have now df by d eta equal to 0, whereas what is the condition in the Blache's equation? Going to 1, u by u infinity equal to df by d eta. Okay. So, now you should understand actually this entire component, okay, is your what, u reference, correct. So, this is the starting point. We assume u by u reference is actually a function of eta, okay, which is nothing but df by d eta. So, this 2 times Grashof number to the power half nu by x should be equal to u reference. You can please check that. Okay. So, we are our u reference definition is 4 times g beta t wall minus t infinity into x. Okay. So, you can replace this with Grashof number. So, g beta into t wall minus t infinity is what? How do you rewrite this in terms of Grashof number? Grashof number into nu square by x cube. Okay. So, therefore, you have 2 times. So, this is local Grashof number. If you take this, this is nu, and this is x square. If you take this is nu by x, right. So, this is nothing but your u reference here. So, in the Blache's case, this was your u infinity at in the Blache's case. Since here you do not have any u infinity, you introduce a reference velocity and this is the reference. So, in the original Blache's case, therefore, eta going to infinity df by d eta was 1. So, u by u infinity, u is equal to u infinity. So, therefore, df by d eta was 1, but here we cannot say u approaches u reference, okay, it is u is 0. So, therefore, df by d eta is therefore 0 here. So, this is the difference also in the boundary condition. Now, if you therefore, look at the boundary conditions, all of them show that this is these are similar equation with the similar boundary conditions. So, you can say that all of them do not involve any x or y components in that. Okay. So, therefore, we can say for sure that we have found a self similar solution to this problem, and the next step is to go ahead and solve it. So, we will once again use the shooting method. That you are so familiar by now, you have been using it for so many different problems, both in external convection as well as in internal convection. Okay. So, you know the equations, can you please convert them into ODEs, ODEs of first order. So, we have a third order ODE, please try to reduce this into 3 first order ODEs, and similarly the energy equation. So, what do you start with? df by is equal to g. This is your first order ODE, and then therefore, next dg by is equal to h. This is your second first order ODE, and then finally, you put it into the master ODE. Okay. So, what will be d square f by d eta cube? dh by d eta, okay, plus 3 times f into h minus 2 times g into whole square plus theta equal to 0. So, this is your third first order ODE. Similarly, your energy equation, we can say d theta by d eta. So, what do you use generally? D theta by d eta is equal to, let us say something like y. Okay. This is your first order ODE. Next you have dy by d eta plus 3 PRF into y is equal to 0. Okay. This is how you have converted. So, now just you can take the vertical plate, discretize this in the eta coordinate system. Okay. So, break this into finite domain with discrete number of points going from eta equal to 0 all the way to infinity will be some large value. Okay. It could be 10, 15, whatever. So, you have points I equal to 1 all the way to I equal to n, right. So, therefore, you will be marching in space. So, these are all first order ODEs. You can use a simple Euler backward differencing, and then you can just simply march in space forward. So, once you know the solution at the previous location, you can use that to calculate solution at the next location and keep going forward till you reach I equal to n. Okay. Now, therefore, in order to march forward in space, you need to know the boundary conditions for f, g and h, right, at I equal to 1, that is at eta equal to 0, then only you can march in a straightforward manner. Okay. Let us see how do we convert this into the equivalent boundary conditions. Okay. As far as f is concerned, so at eta equal to 0, we have f equal to 0 is known. Okay. So, therefore, the first equation can be solved straight away. What about df by d eta? Df by d eta is also known, right. So, this second equation also can be solved. Now, coming to the third equation, we need a boundary condition for d square f by d eta square at eta equal to 0, which we do not know. Okay. So, we do not know, therefore, the boundary condition for d square f by d eta square, which is nothing but h, okay, at eta equal to 0 is unknown, but what we know is df by d eta at eta going to infinity, that is we know the boundary condition for g, which is equal to 0. Okay. This is like your Blasius solution again. So, there you have df by d eta equal to 1. Okay. Same way here also, if you look at for theta, so you know that theta at eta equal to 0 is equal to 1, okay, but you do not know what is d theta by d eta at eta equal to 0. So, this is your y, this is not known, but what you know is theta at eta going to infinity, which is equal to 0. So, therefore, we have to now introduce the shooting method. So, you have to shoot a guess here in this case for h, which is d square f by d eta square, okay. And simultaneously now you have to understand in this case these two have to be solved within the same loop, okay, both with respect to iteration and within the same space loop. Okay. So, it has to be all, both of them have to be solved together. Okay. First you solve the three equations, 3 first order ODEs as guessing some value of theta for example, okay, and then you put that into this and then solve for theta, okay, and now this has to be iterated again and again till you reach a final solution. Okay. So, you have the iteration loop outside and inside you have the space loop within which you have to solve these two simultaneously. So, when you solve this, the problem is, yeah, you do not know again the boundary condition for H here and also for Y here. So, then therefore, you have to shoot a guess for in this case H and also in this case Y, and then use Newton-Raphson to make more accurate estimate of these boundary conditions, provided you satisfy the condition that G at eta going to infinity is equal to 0. Okay. Similarly, here theta at eta going to infinity equal to 0. So, once you satisfy these conditions, that means you have reached a final converged solution. Okay. So, till that point you have to keep guessing the values of both H as well as theta and then solve these two equations simultaneously. So, that means at each point you should be putting the corresponding value of theta and then you get the solution, and then that value of f is put in the equation for theta and solved. Okay. So, once you do this, finally you will have the equations solved for different values of Prandtl number. So, now you will have therefore unique solution for also velocity as a function of Prandtl number, because Prandtl number is the one which decides the value of the temperature profile, and that temperature profile will go into this and decide the velocity solution. So, now Prandtl number will govern both the temperature as well as the momentum profiles. So, I will just give you how the gradients look, the gradient of velocity as well as temperature at the wall, because these are the important quantities to calculate the skin friction coefficient and the Nusselt number. So, and then we will go ahead and see how the profiles of velocity and temperature look. So, Prandtl number, we have f double prime of 0 and then theta of 0. So, finally, this is what you guess, and after you reach a converged solution, this will be your final values. So, if you vary the Prandtl number, so for 4 different Prandtl numbers, if you find the solution by shooting method, you will end up with 0.9862, then 0.6760, 0.41. So, now you therefore see that the gradient of velocity is also a strong function of Prandtl number, unlike the external forced convection. So, that value was simply 0.332. Okay. So, here you have a function of Prandtl number, okay, because it is coupled with the energy equation. So, the corresponding values of temperature gradient . Right. Sorry, this will be theta dash, right. Right. So, you have the corresponding values here, you can just compare for your understanding. So, approximately this is close to Prandtl number 1. So, you have 0.6760 as the value of f double prime. What was the corresponding value for the external post convection flat plate? 0.332, okay. And what was the corresponding value of d theta by d eta for Prandtl number equal to 1? That is also same 0.332, okay. So, these values are now slightly higher than that, but does not mean now the final Nusselt number is going to be larger than the forced convection. We will see that. Now, we will convert that into an expression for Nusselt number, okay. So, can you all do that? So, once you know the temperature gradient at the wall, now you should write down what is the expression for Nusselt number. Yes, so in this case it should be negative, right. So let us say minus of theta dash, that is correct. So what is d eta by dy? 1 by x into Grashof number by 4 raised to the power 1 by 4. Okay. So therefore, if we define a local Nusselt number as hx by k, we simply have minus d theta by d eta equal to 0 into Grashof number by 4 by 4. Okay. So this is your expression. In the case of force convection, what did you have? Minus d theta by d eta equal to 0 into Reynolds number raised to the power 1 by 2. Okay. So you have this factor now by 4, because we have defined this in the similarity variable. So accordingly this will get scaled. Okay. So if you do not use the factor of 4, the value of the temperature gradient will also be different, it will be lower, it will be 4 to the power 1 by 4 times lower. So then therefore you do not have this factor. So now that you have put this constant, so this will be 4 to the power 1 by 4 times larger than the normal case. Okay. So everything gets proportionally scaled. Okay. So the question is, now we have a functional dependence of Prandtl number. So we cannot directly say some value of d theta by d eta there. We have to fit a curve now as a function of Prandtl number. So this was done actually by Ostrach. So initially when Paulhausen solved, he could not solve for so many Prandtl numbers, because he did not have access to numerical techniques. So therefore he stopped with the equation and maybe found just one solution, but it was later Ostrach who extended it to so many Prandtl numbers, Prandtl number much lesser than 1 to much greater than 1, and then he fit a curve to this d theta by d eta as a function of Prandtl number. So according to that, it comes out to be minus d theta by d eta equal to 0 according to Ostrach is 0.676 okay. So this was by Ostrach. You can do a quick check for Prandtl number equal to 0.7 whether you recover the value shown here. If you have a calculator, you can quickly check that. So therefore with this curve fit, we can write down the final expression for Nusselt number. Right. This is your exact solution. Okay. So, now that unlike the case of classical Polausen equation where you have 0.332 times R e power half Prandtl number to the power 1/3. So, now you have a more complex dependence on Prandtl number, and instead of Reynolds number you have Grashof number. Okay. So, this is how the Nusselt number varies. Now, what we will do is also plot the solution for theta and the velocities. Okay. So, once you solve these ODE by shooting method, whatever is described here, you should be able to also plot df by d eta, which is nothing but u by u ref and theta. So, first I will show the variation of theta, which all of you are mostly familiar. So, this is 1 0. So, eta going from 0 to a large value. So, at eta equal to 0, t equal to t wall, right. So, this will be equal to 1, and then for large values of eta it will decay to 0. And what will happen to the temperature gradient with increasing Prandtl number? It increases. Okay. So, this will also shift downward, right. This indicates higher slope at the wall. So, for increasing Prandtl numbers, your temperature profile will be varying like this. Similarly, if you plot your u by u ref, which is nothing but df by d eta as a function of eta. Okay. So, this also shows a functionality with Prandtl number. So, you find that something like this. So, it reaches a value of depending on what you take as your u ref. Okay. So, suppose somewhere here it is your u ref, it reaches 1 here, okay. And if the peak is not your u ref, that will exceed 1. Okay. And similarly with Prandtl number, what happens? What happens to the slope of the velocity at the wall? It decreases. With increasing Prandtl number, the slope decreases. So, therefore, how should the curve shift with increasing Prandtl number? Downward, right. So, this is your increasing Prandtl. Okay. So, for a given value of d eta, so your du will be smaller for this compared to the other one. Okay. So, this is how your similarity solutions look. Now, you should remember that these similarity solutions for natural convection, both velocity and temperature are functions of Prandtl number. Okay. So, we have to be careful about it. So, next thing what I am interested is, if you want to calculate an average heat transfer coefficient, just like we did for the the classical Polausen solution. Sometimes when you solve heat transfer problems, you are not interested in the local heat transfer coefficient, but average values. Okay. So, let us try to therefore start from this point here. Okay. Try to calculate an average heat transfer coefficient, which we will call as h bar, which is nothing but 1 by L integral 0 to L h of x dx, and then define a Nusselt number based on the average heat transfer coefficient and based on the total length of the plate HL by K. So, can you do this and tell me what will be the average Nusselt number? So, if you complete this exercise, so you will find out that you will have 4 by 3 into Grashof number. Now, this Grashof number will be defined based on the plate length. Okay. After you evaluate the integral, you will convert all your x into L. Okay. So, the Grashof number will be defined based on the plate length, and therefore, you will get the expression that the average Nusselt number will be 4 by 3 times the Nusselt number, local Nusselt number, when your x is replaced with L. Okay. So, this is another useful relation that you can use when you are doing calculations for heat transfer rate and so on. So, where you define your heat transfer coefficient based on the entire plate length. So, what was the corresponding relation for the external force convection? Twice of nu at x equal to L, right. So, here we have 4 by 3. Okay. Do you have any questions so far? I hope the procedure is clear, because we have now done enough similarity solutions. So, it is just you have to go through the mathematical procedure and substitution, and you will get it there. Now, what we will do next is move on quickly to the case of constant wall heat flux boundary condition. Okay. So, this is the extension to what Polhausen did. So, he started with the constant wall temperature case, and later on Ostrach completed the solution for different Prandtl number ranges. Now, the extension to this is to find the solution for constant wall flux boundary condition. So, this was attempted by two people, Sparrow and Greg. Okay. So, now similar to the flat plate case where we had constant heat flux boundary condition, now we have to find another similarity variable. We use the same similarity variable more or less there, but the way we have defined our non-dimensional temperature theta. Okay. So, in the constant wall temperature case, we use this definition, and in the constant heat flux case, since T wall minus T infinity is not a constant, we have to replace this in terms of heat flux, which is known, which is fixed. So, similar to the flat plate case, so what we can do is assume this is your T wall, this is your T infinity, and therefore, we can relate some kind of scaling to convert this temperature difference into heat flux using the Fourier conduction equation. So, what we can say is that your q double prime is equal to minus k say dt by dx. Therefore, this can be written as T wall minus T infinity. The order of magnitude of this will be q double prime into x by k. We are just looking at the order of magnitude. So, therefore, we will write theta here as T minus T infinity by instead of T wall minus T infinity, we have q double dash. Now, your coordinate, this is actually y and this is your x. So, therefore, we have to be careful, we will be using y here. Okay, by k. So, this is how we try to transform temperature, dimensional temperature T to a non-dimensional temperature theta. Okay, just doing order of magnitude analysis. now we have to also find the right definition of Grashof number. Okay. So, your conventional definition of Grashof number is also based on temperature differences. Now, how do we convert again this temperature difference into what is known to us in terms of heat flux? Again we will use a similar scaling. Okay. So, we can simply write therefore, T wall minus T infinity as something like Q double prime x by k. So, x and y, they are just the order of magnitude of x and y are comparable now. Okay. So, we will just interchange them. So, that we can define a Grashof number, we will use Grashof number star now to differentiate this from the conventional Grashof number. Now, this will be based on your heat flux. So, therefore, this will become Q double prime and then what will be x power 4 by nu square k. So, this will be the modified Grashof number, this is called the modified Grashof number for constant wall heat flux boundary condition. So, you understand. So, we know what is the wall heat flux. If you, so we are replacing y with x. Now, we cannot use in the Grashof number y into x power 3, you understand. So, we are just doing some scaling where we say the order of magnitude of x and y are kind of similar and therefore, we are converting that also into x.
So, can we use y there or some delta or something?
Why do you want to complicate the definition of Grashof number? So, the Grashof number is only based on one local coordinates. Why should we use y times x? How do you then compute your graph? Is it a 2-dimensional variable? Okay. So, Grashof number is just a local coordinate which is attached to the plate length. Okay. So, we cannot therefore define a 2-dimensional Grashof number here, it is like defining a 2-dimensional Reynolds number. Okay. So, therefore, this is a definition. Okay. There is nothing wrong in defining a Grashof number the way you want it, provided it is dimensionally consistent. Okay. So, this might not be an exact transformation of your conventional Grashof number, but you say get a non-dimensional group. Okay. So, that is all you have to be worried about. We should not think about complicating it further, and all you need to do is once you know your heat flux, put it into this, and therefore, now you have a local Grashof number varying as a function of x. So, this will be the starting point for defining the similarity variable, right. So, and once again, now when you look at the similarity variable, what was the similarity variable in the constant wall temperature case? So, we have eta equal to y by x, your normal Grashof number by 4 raised to the power 1 by 4. Now, if you simply replace this normal Grashof number with Grashof number star, what happens to the similarity variable? It becomes y.
Constant times y.
Yes. So, that means you will not find the correct similarity variable because there will not be any function of x. Now, your Grashof number star is x power 4. So, x power 4 1 by 4 is x, x cancels. So, you will have a similarity variable which is only a function of y, which is not possible, correct. So, therefore, now accordingly you have to modify the definition of similarity variable for this case. So, how Sparrow and Greg did it was just changing the 4 to 5. Okay. So, now the functional dependence of eta on x and y are retained. Is that clear? Okay. If you use the default similarity variable, you cannot find a similarity variable for this. Therefore, you have to modify it a little bit. Okay, I mean, if this is the right modification, you should be able to find a similarity equation. So, that we will check how we convert this into a similarity equation. So, but basically this is the starting point. We redefine the definition of similarity variable in the constant heat flux case, because we have now defined a new modified Grashof number. Okay. So, please keep this point in mind, and then in the next class we will continue from here. Now, the rest of the rest are details. So, once you identified the similarity variable, then finding velocities, substitution, they are all the standard procedures. And then maybe you can do this as an exercise and check what kind of similarity equation that you get. Okay. So, then we will meet in the next class.